what is the free energy or what kind of phase transitions that we can expect in this system as a function of temperature. So it's not particularly surprising that because there's a competition between two locally stable saddle points, there's going to be a first order phase transition, which is the famous Hawking-Page phase transition. So to complete things off, I'll just mention, and I won't give the calculation, is that the free energy of thermal AdS, as kind of pointed out earlier, is that it's non-zero and it requires to be calculated carefully in gravity. This calculation was done, and there is actually an interesting point about this. So again, thermal AdS doesn't have any interesting thermodynamics because its time circle or the temperature circle doesn't shrink. It's just kind of multiplying the geometry everywhere. So if you look for any non-trivial temperature dependence, there is none. Okay, so the free energy is just a constant for thermal AdS. It's exactly the same as in the three-dimensional example earlier. And it's given by this specific number, and this specific number is actually a significant number. So it's a holographic computation by Balasubramanian and Krauss. That's 99, I think. Okay, and this number is an interesting thing, that this number 3/16 you get by honest holographic gravity computation, just calculating the free energy of the solution, evaluating the action by adding counter term after adding counter terms, etc., and doing things correctly. And this actually matches on the dot with the Casimir energy of free fields. Free n equals 4 super Yang-Mills fields on S3. Okay, so if you do this bubble calculation and you just calculate the free energy for just the free fields in the lambda equals 0 theory. So this is lambda equals 0, and this is of course lambda tending to infinity. This 3/16 is exactly the number that you will get once you calculate these things by zeta function regularization. So that matches between the two sides, and it's related to the fact that you get the same result for 0-Tooth coupling and infinite Tooth coupling is related to an oft-made statement in string theory that AdS5, the fact that these two match is related to the fact that AdS5 is stable against stringy corrections. Which means that, I mean, if you move away from the infinite strong coupling limit, to move away from the infinite strong coupling limit, you have to include stringy corrections. And the point is that AdS5 as a geometry, because of all its symmetry and maximally symmetric properties, will not get modified at any order in string perturbation theory. So there's nothing that's going to happen to it. And so these Casimir energies match between weak and strong coupling. So I will also not write down what is the free energy for the big black hole solution. It's easily computable because of the reasons that we have mentioned already. Once you compute the entropy, you can calculate the free energy by integrating the entropy, and now you know the constant also that you need to fix. Yes?
But now you put it in a box, so it's not obvious that it's still insensitive to the stringy corrections.
I'll say that again. What was it?
Now you put the boundary on the S3.
Yes.
So it's not clear why the stringy corrections will not be important.
No, I think it doesn't, the fact that you put the theory on S3 doesn't do anything because it's still...
It's invariant.
No, because the geometry is still AdS5 cross S5. It's pure, this is just AdS5 cross S5 written in global coordinates.
Okay.
Okay. What we call thermal AdS is just happens to be AdS 5 cross S5 in global coordinates, with the extra fact that the thermal circle is the time circle is Euclidean and periodically identified. Okay, so it's still just AdS 5 cross S5, and it has all the properties that expect it. It's AdS 5. It's no different. And it has all the supersymmetries. It's just that they are realized in different ways. The supersymmetry. There's no. So in that sense,
putting the system in the box doesn't break symmetry.
but it's like what I said. If you take n equals 4 theory on the plane, right? Since the plane is related to S3 cross R by a conformal transformation, you're not changing the theory. It's some way you're just changing the quantization. It's like taking 2D CFTs on the plane and doing radial quantization, if you want, you can think of it that way. And which means that you're defining the Hamiltonian as this. The Hamiltonian is equivalent to the generator of dilatations. So you're identifying the Hamiltonian system as the generator of dilatations. And so you're not changing the theory, you're not even changing the bulk. What you're changing is basically, you're doing this conformal transformation, and what you're changing is the definition of the time evolution operator. The Hamiltonian is actually now identified with dilatation.
The differencing of the boundary condition for fermions and bosons in time direction breaks supersymmetry.
Yes, it does, but in the bulk, that's a good question. And it's a tricky question to answer actually, and I may not be able to answer it satisfactorily. That difference actually just shows up when you're in the black hole phase, when the thermal circle shrinks to zero size. And in fact, the black hole solution can only exist if the fermions have the wrong periodicity condition. In other words, they're anti-periodic. So in this, you can derive this without ever talking about temperature. You can derive this by just taking the zero temperature. You don't have to talk about it, or you will get this result. Okay, so you can calculate the free energy. So all that's going to happen is that for whenever the free energy of the big black hole is greater than 3/16 n squared, we will find that the big black hole is subdominant and thermal AdS dominates the ensemble, and vice versa. So when does this happen? This happens for all temperatures greater than 3/2 pi. So all of this is quite easy to figure out. And then conversely, the big black hole dominates the sorry, I got that the wrong way around. So the big black hole dominates the ensemble when temperature is greater than 3/2 pi, and the temperature at which the two switch is the famous Hawking-Page temperature. So Hawking-Page is 3/2 pi, and in fact you can sort of see that this phase transition is the first order phase transition, because if you calculate the free energy, so first we know that for T less than T Hawking-Page, the free energy, since the ensemble is dominated by thermal AdS, the free energy is just 3/16 n squared. For T greater than T Hawking-Page, the free energy is going to be the free energy of the big black hole solution, and we can look at what happens when the temperature is just slightly above the Hawking-Page temperature, and you find that the free energy of the big black hole solution looks like n squared times 3/16 minus etc. So close to the Hawking-Page transition, just above it, the free energy of the big black hole solution clearly is below the free energy of thermal AdS, which is 3/16 n squared. There's a minus sign. And what it's also saying is that if you calculate the free energy is continuous, okay, as it must be across the transition, but the derivative of the free energy is not continuous. So the specific heat is discontinuous, so it's a first order phase transition. So first derivative of free energy of F is discontinuous. Okay, so this is a first order transition. What's also important to note is that across this transition, if you subtract out this 0 point energy, the Casimir energy, right, which is a reasonable thing to do, it's just a 0 point energy. If you subtract it away, you're basically saying that the energy, free energy of the system scales by or increases by, changes by an amount order n squared. Okay, it changes by an amount order n squared, which is not surprising, and hence it suggests that you should think of this phase transition as possibly some kind of a deconfinement transition. But that's a very loose statement. And there is a more precise way of making it, of saying this, that this is a deconfinement transition. So, since delta F is of order n squared, this is suggestive that there is a drastic change in the number of degrees of freedom. But this should be taken with a grain of salt, because after all the theory was not confining to begin with. It's a conformal field theory in finite volume. Okay, so suggestive of the second important point to note is that we are thinking of a system in finite volume. And in finite volume, we are led to believe that there are no phase transitions. Okay, so this phase transition that's occurring is clearly an artifact of taking the n goes to infinity limit. Artifact is probably sounds like a negative word. I would just say it's a feature of the n goes to infinity. So, so what this is saying is that this is a sharp phase transition for n tending to infinity. And at finite n basically thermal AdS and big black hole both will coexist. Okay, and you can't really say that you're in the black hole phase or in the thermal AdS phase. Right. So finite n effects will smooth out the phase transition, and the large n limit plays the role of a thermodynamic limit. Okay, so once you have this picture in mind that you've got these three different kinds of saddle points in the gravity partition function, I mean, one is always tempted to draw some kind of free energy, okay, per degree of freedom versus something which we don't know what it is yet. I mean, there's a phase transition, so we expect that there's some kind of order parameter. Okay. Now the point is that what's this free energy as a function of order parameter? If you were doing ordinary field theory, say lambda phi to the fourth, and you were studying some kind of discrete symmetry breaking effect as a function of temperature, like for example in the Ising model, you would plot something like you would plot the free energy versus the magnetization, and then you would see what the hills and the valleys in the graph look like. So we are here dealing with a system which is described by gravity. Okay, and there is some order parameter in the system. I don't know what it is, but what I do know is that there are three saddle points. Okay, the three saddle points in this gravity partition function. So we can sort of guess that if we could plot some such thing, it would have to look like this. There would be this saddle point which we will call thermal AdS, and I will draw it exactly at 0, because thermal AdS seems to do nothing interesting. It seems to have a free energy that's just constant as a function of temperature. So let's take that as the 0 reference point. There's going to be another saddle point there and another saddle point there, and this is what we call the big black hole, and this is going to be the small black hole. And if I could draw something like a potential energy type graph, I mean, it would have to look something like this. Okay? It would have to look something like this for low temperatures, T less than T Hawking page. This is what you expect of most sensible systems, that you have these two locally stable states, and then for low temperatures, this one has lower free energy, it dominates. This one is locally thermodynamically stable, this one is unstable. And then at high temperatures, they just interchange roles. So if you did the same thing, okay, the free energy over n square versus an order parameter, then at high temperatures, T greater than T Hawking page, what you will find is something like that: small black hole, big black hole, thermal AdS. Okay? And if you keep increasing the temperature further and further, it's clear what's going to happen eventually. There will be some asymptotically high temperature at which the small, this curve is going to keep coming down. At some point, the small black hole saddle will merge with that. That's the only thing that can happen to these kinds of functions. And it will cease to be a stable saddle. Okay? That is actually an interesting temperature. In string theory, that temperature is what we would associate with the Hagedorn temperature of string theory. Okay? So that's just, I'm mentioning that as reference because as something to remember, because we will come back to that point in a bit. So, if you increase the temperature at asymptotically high temperatures, we expect that eventually this saddle point will just disappear. The two will, thermal AdS and small black hole will merge. And disappear. Okay, so if you drew the graph at asymptotically high temperatures, you would expect that there is only one true saddle point. It's a kind of thing that you would expect. Now, that is something that's called a Hagedorn temperature because, well, the significance of that is that suppose you forced yourself to stay in this phase. It's like some kind of, this is like a metastable phase at high temperatures. If you force yourself to stay in that phase, there's no black hole in that geometry, there's no horizon. So in that geometry, the thermal circle never shrinks to zero size. Okay, never shrinks to zero size because that's thermal AdS. But now you might start wondering what happens as you increase the temperature to such a high value that the size of the thermal circle, okay, the size becomes comparable to the string scale. Because the string scale is a small scale set by L string or alpha prime, and there must be something interesting happening when the temperatures start when the temperature which is, so temperature goes to infinity is beta going to 0, so that means thermal circle shrinks to 0 size. So when the thermal circle is shrinking and becoming smaller and smaller and becoming comparable to the string scale, what can happen is that winding modes of the string around the thermal circle can become light, and in fact eventually they can condense. The condensation of the winding modes is precisely something that one associates to the formation of a black hole. Condensation of winding modes is actually related to something like the expectation value of a Polyakov loop operator. So I just wanted to mention that it's not significant at this stage, but the point is that if you sit in this phase and try to heat the system up, eventually this phase has to disappear because at arbitrarily high temperatures you expect that winding modes of the string will become relevant, they will condense, and actually this phase should cease to exist. Okay? That's the temperature at which that happens is what's known as the Hagedorn temperature. And that Hagedorn temperature also is the temperature, is kind of universal because it's also the same effect is expected if you take string theory in flat space and you just heat it up, there is a Hagedorn temperature. So that Hagedorn temperature is dictated by string scale physics. So this happens at T Hagedorn, which is of order square root sorry, 1 over square root of alpha prime, which if you then convert it into gauge theory parameters using the dictionary that we spoke about, this becomes the 't Hooft coupling to the 1/4 power. Okay, so in the large 't Hooft coupling limit, the Hagedorn temperature is very high. It's very high. But it's not a phase transition temperature. It's just a temperature at which these two saddle points cease to exist. The phase at all high temperatures above the Hawking-Page transition, the thermodynamics is completely always dominated by big black hole. There's no phase transition above the Hawking-Page temperature. But there is an interesting temperature above the Hawking-Page temperature, which is at these scales. Okay, so there, what we see is that there is some non-trivial thermodynamics, and now the question is, what is the correct order parameter? Because I plotted these things, but I didn't tell you what the order parameter must be. So there is actually a natural order parameter from the gravity side. And it's kind of evident geometrically, but then it of course has a very clean gauge theory interpretation, which is very, very precise interpretation actually. So what's the order parameter? Well, so the hint comes straight from geometry. And it is that if you are in the thermal AdS phase, topologically thermal AdS is actually S1 cross the 4 ball. Okay, so global AdS you can think of, I mean it's spatial slices, you can think of it just as spatial S3s filled in. So it's like the ball, I guess that's the 4-dimensional ball, times an S1. The big black hole is different topologically because the thermal circle shrinks to 0 size at some point. Okay, so if we actually plot what's happening to the thermal circle in the big black hole, as we have discussed so many times, so this is versus some radial direction, this is the horizon size, that's infinity, and this is tau, the thermal direction. This circle shrinks to 0 size at the horizon. So topologically this is actually a disk. This thing is a disk, and this space is topologically a disk, 2 disk times a 3 sphere. Okay, so at each location of the disk there is a 3 sphere. So if you did